A vital part of chemical reactions is the transfer and movement of energy. Energy is a word that we've all used before, and the physics definition of it goes along with the connotations you already have of the word. It is the ability or potential to do work. If you have a lot of energy, you can move around and do a lot. If you do not have enough energy, you can't. Energy isn't just you having the ability to run around or not, though. It goes down to the atomic level and the movement of atoms and forming and breaking chemical bonds. Anytime matter moves, work has been done. So a chemical reaction requires energy. Actually, anytime matter interacts and moves, energy is transferred back and forth. How is energy involved in chemical reactions? Let's think about a few examples. Plants bond carbon dioxide molecules to water molecules to produce glucose during photosynthesis. Why can't they do this without light? The answer: light is a form of energy, which plants use to fuel the reaction between carbon dioxide and water. In particular, they use it to break the bonds holding the two types of molecules together and to form the bonds of the new molecules. For another example, to light a candle, you must add a flame from another match or lighter. But after the initial flame has been removed, the candle continues to burn. How come? Fire produces heat and light, both are forms of energy. Where does the energy come from? The atoms in the wax are held together by chemical bonds. Once that initial energy from the match was added, those bonds begin to break. As they break, they release more energy, which keeps the flame going and fuels more molecules in the wax to break down. So the answer to that first question, how is energy involved in chemical reactions, is that it is transferred, released, or absorbed whenever chemical bonds form or break. This causes some reactions to take place slowly, some to take place very quickly, some to require constant inputs of energy, and some to release energy to the environment. To break a chemical bond, you need to add energy. Things don't just break on their own. If you drop a glass, it breaks when it hits the ground because a lot of energy entered it all at once. If you're going to tear down your old shed and build a new one, it doesn't just disassemble itself. You have to grab the sledgehammer and smash it. You have to add energy. Compounds work the same way. To break them apart, you have to add energy. When compounds form, they will store some energy away and release some to the environment. Sometimes, the product compounds will release a lot more energy than they stored away. In that case, the reaction will give off heat or light, like a burning match does. Other times, it will store away more energy, in which case little is given off. If a chemical reaction absorbs more energy breaking its bonds and forming its products than it releases forming its products, then the total movement of energy is into the reaction. These reactions are called endothermic reactions because heat or energy moves inside. Endo means inside. Photosynthesis is an example of an endothermic reaction. The opposite situation, where more energy is released to the environment than is absorbed to break bonds or is stored in new bonds, is called an exothermic reaction. Exo meaning outside. So heat or energy exits the reaction. Cellular respiration is an example of an exothermic reaction. In this reaction, energy stored in glucose molecules is released to fuel our bodies. Some reactions will occur spontaneously without any input of energy because the bonds holding the reactants together are unstable. But most of the time, even in exothermic reactions, an initial input of energy is needed to get them started. The amount of energy needed to start a reaction is called its activation energy. Looking at the pictures, the y-axis or the vertical axis shows how much energy is in the reacting compounds, and the x-axis or the horizontal one shows the progress of the reaction, basically time passing. If you follow the line, you can see the energy as it rises and falls. Notice that in both reactions, there's a bump in the middle, somewhere between where the reacting compounds are called reactants and where they become products. the top of the bump is the activation energy. The reactants had to gain that much energy before the reaction could start and they could turn into the products. Focusing on the first picture, you should notice that the reactants are higher than the products. This means that the energy was lost or given off during the reaction. So this would be an exothermic reaction. Looking at the other one, the products are higher than the reactants. This means that the involved compounds had more energy after the reaction than before. So they took that energy from the environment and stored it. This makes this an endothermic reaction. Since reactions need added energy to take place and have to move atoms around, forming and breaking bonds, they take time. The speed at which a reaction takes place is called its reaction rate. Reaction rate is affected by how exposed the reactants are to each other. The easier it is for them to interact, the faster the reaction can take place, and the amount of ambient energy available to start the reaction. The more energy there is available, the faster it can go. Based on this, there are a few things we can do to make reactions happen faster. First, we can increase the temperature, which increases the amount of energy available. Stirring or shaking will do this as well. Second, we can increase the concentration of the reactants. Adding more of them increases the likelihood that they'll interact. We can increase the surface area on which they react, giving them more space to interact. We can add a catalyst, or we can remove an inhibitor. All of these ones will increase how exposed the reactants are to each other. Two terms from that list that we probably need to go over are catalyst and inhibitor. A catalyst is anything that lowers the activation energy required to start and maintain a reaction. Usually, they are compounds that grab the reactants and hold them together. They aren't part of the reaction, but they help it along. If you're making pancakes, you bring the eggs, flour, milk, and sugar together. So you are a catalyst. You may have heard the word enzyme before. Those are just protein molecules that act as catalysts. Inhibitors are just the opposite. They are compounds that get in the way of a reaction and slow it down, increasing the amount of energy needed to start it and maintain it. The antihistamines that some of you may take to slow down your body's reaction to allergens are inhibitors.